All right, so here we have an exercise where we need to implement the power function. So basically we're going to be given a float x and an integer n, and we need to return x raised to the power of n. I have some examples here looking at the constraints. X is just some float here, n is some integer, and n can be negative. Okay, so n is an integer, so that's good. Either x is not 0 or n is greater than 0, so we don't have to worry about raising 0 to a negative power, because that would involve dividing by 0, so that's not defined. And we also don't have to worry about 0 to the power of 0. Okay, so basically we don't have to worry about any of like the undefined stuff. So that's good. But basically, we can think about, okay, what would be like a simple way to implement this? So we see here, the one thing we need to keep in mind is that n can be negative, but we know by the way that exponents work is that negative exponents, it's just dividing by a positive exponent. So like 2 to the power of, like x to the minus n is just 1 divided by x to the n. So we really only need to implement the case for positive exponents n, and then we could just use like division, or 1 divided by that result if we're dealing with a negative exponent. Okay. So let's see here. How am I going to So we could do like a very simple implementation where you just multiply x by itself n times, but you deal with n being negative first. So let's do that. So if n is negative, then we make it positive and we just replace x with 1 over x. Because, yeah, so, yeah, x to the minus n. Let's just say n is greater than 0. X to the minus n is going to be 1 over x to the n, which is the same as 1 over x to the n. Well, we don't even need this. So basically, we can change the sign. I don't like that. We can change the sign of, we can flip the sign of n and put x in the denominator. Okay. So that's what we're doing here if n is negative, because we want n to be positive. Okay, so then we just start with our result being 1, and then we can just multiply result by x n times. And we just return the result. Okay. So this is like a very simple implementation. And we can run it, and okay, so it seems like it works. So let's submit this, and what's going to happen? It's annoying that this takes a little bit long to get to this. Okay, so time limit exceeded. So what happened here? So x here, okay, so part of the issue here is that x is like really small in this case, so when we do the division, it becomes really large. But you see that, so there's two things that we could do to try to solve this. Is we could try to make it so that we don't have to, maybe we can do this division, maybe we could do this somewhere else in the process, and thus speed it up in that way. Or maybe this thing is just slow. Like maybe being able to deal with a value of n this large. Oh, wait, no. Ignore the x thing. N is just really large here. So, yeah, we need to be able to deal with, and also like in the description it says this, like n can be really large. So we need to have some way to deal with this. So this isn't super fast. And depending on what, how much you've studied algorithms, This implementation is pretty slow because, like in terms of complexity, it's the complexity is big O of n, because you have to do this multiplication n times, and so we can think about this problem. Think about is there a way to do this without using without having to multiply it n times? And the key here is we could rewrite x to the n as x to the n over 2 times x to the n over 2. So this actually makes our lives easier because we only need to compute x to the n over 2 once and then multiply it by itself to get to x to the n. And so we want to have our solution use this factorization to our advantage. And basically this comes down to recursion. And so basically we want to use this, and so we want to think about, okay, so if we were to actually implement this, like how would this look? Because basically what we could do here is we could just say like, okay, so my POW, you send an x and then you send an n. Well, what if we just have it return? This is going to be very simple, but so just think of this as like pseudocode for now. But what if we could just like return my POW of x n over 2 times my POW of x n over 2? Or really what we would do is we would do half POW is going to be this. And so we compute it once, and then we multiply it by itself, and we return that. This is basically what we would like to do, but there's a couple tricks or a couple things we need to keep in mind. First of all, with the way that LeetCode works, you can't just recall this. You can't call this function recursively. You would need to put another function inside here, and then call that function recursively. And so I'll write that out when we get to that. So that's one thing we need to keep in mind. Also, we need to keep in mind like the base case. So if n is 0, then we just return 1. Because if we're doing recursion, we need to give it some condition to halt. And so we're going to halt when the exponent n gets down to 0, because when we get there, anything to the power of 0 is 1. Well, x is not 0, so anything that's not 0 to the power of 0 is 1. So we're good. Okay, so that's that. The other thing that we really need to think about is the fact that n is an integer, and here we're taking n over 2. So if we want to feed it back in, we need to feed back in an integer. But we can just think about it. So like, if n is even, then this works fine. We could just take x to the n over 2, and I'll just say squared, because we're just going to multiply it by itself. And this will work because if n is even, then n over 2 will be an integer. If n is odd, then we can't do that. And so what we can do is we can use this floor division. So this is just, so n //2, this is n, it's the greatest integer, which is less than or equal to n divided by 2. So when n is even, then this is just this is pretty straightforward when n is an integer, because for integers, if n is even, then this is just equal to n divided by 2. Except that it will return an integer rather than a float, but that's fine. Which is actually what we want, because we want n to be an integer. Whereas normally if you use just a single slash in Python, it will just return a float by default, even if it's a float representation of an integer. But here, if n is odd, then this ends up being n minus 1 over 2 plus, okay, so, okay, so like if we have 3, 5, 7, so we have n slash 2. So 3 divided by 2 is 1.5, so then this would become 1. 5 divided by 2 is 2.5, so it would become 2. 7 divided by 2 is 3.5, so this would become 3. And so basically it's n minus 1 over 2. And another, so this is also equal to n over 2 minus a half. And so you could also write this n over 2 equals n slash 2 plus a half. Okay. But in any case, so basically what we're going to want to do is we're going to want to rewrite this using double slashes, because that will make our lives easier. So here, this is the same as x to the n slash 2 squared. And that's because when n is even, n divided by 2 is equal to n slash 2. The only difference is that Python returns an integer rather than a string, rather than a float, which is actually what we want. For an odd, so we have x to the n equals so this is going to be x to the n over 2 squared. So this is going to be x to the n slash 2 plus a half squared. So this is going to be x to the n slash 2, x to the 1/2 squared. Okay, so then this is going to be x to the n slash 2 squared times x to the 1/2 squared. So this is x to the n slash 2 squared times x. Okay, so basically this is what it comes down to. If n is even, then x to the n, we're just going to take x to the n slash 2 and square it. If n is odd, we're going to do that same thing, but then multiply by an additional factor of x to account for the differences that were introduced when we took this floor division. But basically, this is the formula that we need to use. Okay, so let's actually implement this. So okay, so how I should spell correctly. Yeah, and so x will be a float, n will be an int, and we will return a float, just like with the original. And so basically this is going to be the same function that we implemented before, but this time we're writing the function on the inside so that we can call it recursively. Okay, so again, because we're doing this recursively, we need to take care of the base case. So if n is 0, then we're done. We can just return 1. Okay, and then if n is negative, then again, we can do this thing where we take x equals 1 over x, and then n equals minus n. And then what we're going to do is we're going to take half pow, and this is going to be recursive pow x n divided by 2, floor division. So this is what we talked about here. We're doing this thing. Okay. So, and we're calling this half pow because it's just x to the power of half of n plus floor division. Okay, so now we need to determine if we return this squared or this squared times x. And that depends on whether n is odd or even. So if n is even, meaning that dividing that n mod 2 is 0, then we can just return half pow squared. Otherwise, n must be odd, and so we return half pow squared, and I'll just put the x out front here. X times, oh, that looks ugly. There, now it doesn't. Now x times half pow squared. Okay, cool. And then what we need to do is at this level, we need to return recursive pow xn. No, there, this level, right? So we're basically defining this function and then we have to call it because we have to define this fully before we can like get the recursion to go. What I had originally done, which does not work, is just done this, and then, yeah, because you need to call, yeah, so this just doesn't work with the way that LeetCode is set up. You have to do this. Okay, and so then, let's go ahead and run this just to make sure that I didn't do anything wrong. And then let's submit it. And make sure, again, that it works. Okay, cool. And so now what I want to do actually with this is I want to explain why did this work. And so going into like algorithm theory, this is an application of the master theorem. So we have just this. Okay, so basically, suppose we have an algorithm and we have a function t of n where n is the size of a particular input and t of n gives you the runtime of the algorithm depending on that input size. And so if we have a recursive algorithm, then we can generally write t of n in this form. Because basically what we're doing here with the a times t n over b is that we're breaking t into, instead of doing this algorithm a single time with a input of size n, we do it a times with inputs of size n over b. And then we add some additional term here for anything else that needs to be done. Okay, so, and then you use the values of a and b to compute the complexity using this stuff. So let's think about our exercise here. So the runtime of recursive pow based on the input n, well, what you have to do is you have to run this function again, but with an input of size n over 2. And then once you get that, you have to multiply it by itself. Okay, so we can think here like the b value would be 2 because the input of the function inside here is n over 2. So, and to get n over 2, we would have b equal to 2. Now a, how many times do you need to do this? Well, if you first look at this, you might think, okay, well, half pow, we have to do it twice, so a is going to be 2. But that's not what we're actually doing here. We're using the symmetry of this problem. And so we just compute half pow once and then divide it by, and then multiply it by itself. So when we multiply it by itself, we only have to compute it once. And so a here is actually going to be 1. And then f of n is anything else that needs to be done. And so what here, for this case, there's nothing else that needs to be done. For this case, there is something else that needs to be done. We need to multiply by x. But this additional work of multiplying by x, this does not depend on the size of the input n. This is just going to take the same amount of time regardless of n. And therefore, this is a constant time operation. And so in this case, f of n would just be big O of n, big O of 1, because it takes constant time. Okay, so just to write this down, we have t of n equals a t n over b plus f of n. And we have a is 1, b is 2, f of n is big O of 1. Okay, cool. So now, the other thing that we're going to need here is we're going to need some critical exponent c, which is log base b of a. So c, or c crit, is going to be log base b of a. So this is log base 2 of 1. But regardless of the base, log of 1 is going to give you 0. So this is 0. Okay, so now we look through these cases and see which one applies. So there's this case where f of n is big O of n to the power of c for some c strictly less than c crit. Well, c crit is 0, and f of n is big O of 1, and so this is not n to a negative exponent. And so this is this case does not apply. So we're not in case 1. Then we look at case 2. Okay, so f of n is big O of this thing. So f of n is, in our case, f of n is big O of 1. So this is O of, okay. And I know I'm doing like abusive notation by like mixing up the O and the theta, but just don't worry about it. I mean, you can read into this more if you want to be like absolutely sure that what we're doing is technically correct, but you can also trust me that it is. But yeah, so theta of, that is a theta, right? Yeah, pretty sure it's a theta. It's got to be a theta. Okay. N to the power of secret. Okay, so big O, so 1. So n to the 0 is going to be 1. And then log n to, well, if we want to get 1, we should raise this to the power of 0 as well. Okay. And so 0 is equal to secret, so this matches. And then for some k greater than or equal to 0, well, this value of 0 works. Well, this value here, 0, is greater than or equal to 0. So this works. Okay, so we are in case 1. Okay, so then the algorithmic complexity of our algorithm, the complexity of the algorithm. So T of n is going to be theta of n to the secret, so that's 1, times log of n to the power of k plus 1. So here, in the statement of this, when we were writing this out, we set k to be equal to 0. So this is going to be 0 plus 1, which is 1. So it's just going to be log n to the power of 1. So that's just log n. Okay, so the complexity of this algorithm is log of n. And this makes sense intuitively if you have read through like the proof of the master theorem and have worked with some examples, because basically what we're doing is every time we do a recursion, we're splitting the problem in half. And so if you're splitting a problem in half recursively, that's basically logarithmic. And I think we can even like write this out, because if you think about this, like we could write out a table. Like we have n. Let's write it like this. So n, and then we have number of function calls. Pretend that I wrote that legibly. Okay, so n. So if n is just if n is 0, then we have to just call it the one time, and then we're done. If n is 1, then we have to do it again for 1 floor division 1. No, 1 floor division 2, which will give us 0. Okay, so for 1, we're going to have to do it 2 times. And then if n is 2, then we're going to have to call it once to get from 2 to 1, and then once, wait. Yeah, we're going to have to call it like the initial time just to set it up. Then you're going to have to call it again to go from exponent 2 to 1. Then again to go from, oh, no. Okay, you call it the first time to go from exponent 2 to 1. Then you call it again to go from exponent 1 to 0. And then you have to call it that final time using exponent n equals 0. So this is 3 function calls. When n equals 4, then we have to call it once to get down to 2, once to get down to 1, once to get down to 0, and then call it final time when it's 0. For when the exponent is 8, we have to call it once to get down to 4, once to get down to 2, blah, blah, blah. Once to get down to 4, once to get down to 2, once to get down to 1, once to get down to 0, and then do it again, 1, 0, 5. And you can see how this is shaping out. So what we have is that if this is, if m, if we call this m, or this is m, then this is going to be 2 to the power of m minus something. Is it 2 to the power of m minus 2? Yeah, because 4 is 2 squared. Eight is 2 cubed, 16 is 2 to the 4th. It's 2 to the 5th. Yeah, so it's 2 to the m minus 2. And so if you take log base 2, then you get log base 2 of 2 to the m minus 2 is going to be m minus 2. And then this is going to give you just log base 2 of m. And so if you really wanted, what you could do is you could do m and then log base 2 of m. You could do 2 plus log base 2 of m. And this 2 is just a constant. And so basically, if the input, if we're using the variable n here, let's do that. So this is going to be n, and this is going to be 2 plus log base 2 of n. So basically, we can see here that if the input is the integer n for where n is a power of 2, then we can see here that the number of function calls is going to be 2 plus log base 2 of n. And the 2, this is just a constant, so that's not going to matter when you do like an asymptotic analysis of this. But basically, this shows you that the complexity based on n, or this gives you some heuristic indication that the complexity is indeed log of n, and in this case, it's log base 2 of n. But yeah, so basically, you can use the master theorem to and the important thing here is that this is faster than the previous algorithm that we were doing, because the previous algorithm, here, this algorithm is theta of log n, and the last algorithm that we did, where we were just looping through n, was linear, because you have to you would have to do the multiplication once for every the number of times you would do the multiplication is precisely n, and so the algorithmic complexity was linear in n, we know that linear complexity is much longer than logarithmic complexity. And so this gives us the theoretical support that this algorithm, or this proves that this new algorithm that we've written that uses recursion is faster than the previous algorithm that we tried to implement. And that's why the code doesn't, we don't get a runtime error. We don't, that's why this code actually finishes running, is because the algorithm is much, much faster. But yeah, so that's how you come up with the solution. That's how you implement the solution. And that's how you prove the algorithmic complexity of the solution. And that's it for this exercise.